Thank you. So, yeah, thanks for the invitation for this meeting. So I'd like to talk about some of my recent work with Professor Yao on using singularity theory to study or classification mainly for 5-dimensional angle-swung CFT. And the motivation is just try to classify or find as large as possible class of 5-dimensional angle-swung CFT. So using M theory, simple singularity, and I'll send it back to some of the properties which I always feel confusing. Hopefully the geometry can tell us more about the properties of the series. So I'd like to start with some introduction about some of the generic features of 5-dimensional angle-swung CFT. And you will see some of the interesting features of the series. This series has 8 supercharge. That's like 4-dimensional angle-2. So the representation theory of the corresponding 5D angle-swung conformal algebra has been studied recently by Clay, Cordova, Thomas, and Kang-Tredegar. Although many of the properties, many of the results, I guess, should be known to experts in the 90s, I guess. Especially, I guess, to Nati. I guess he knows all the answers, although he never proved it or written down the derivation. So the bosonic symmetry proof we have SO25 conformal symmetry. And there's a R symmetry. So only one SU2R symmetry. And sometimes we can have a flavor symmetry. That's very crucial. But sometimes we can have theory without any flavor symmetry. But the representation theory of this 5D angle-swung superconformal algebra has been classified. And the highest weight states or highest weight supermodifier is labeled by this quantum number, where the delta is the scaling dimension, and those are spins, and these are the SU2R quantum number. And the short modifier, or BPS modifier, which is always the first question you like to ask for your supersymmetric theory. So for any supersymmetric theory, this type of operators, which are annihilated by some fraction of supersymmetry, is always the first order question you like to ask or you like to understand. And but for us, there's only one type of interesting modifier, It's called D-type multiplier in the papers I just mentioned by Richard and all. And what's it called? This operators, this multiplier has a labeling as follows. The no spin, so it's a scalar. The lowest component is a scalar, and only SU2R quantum number and the scalar dimension is related to the SU2R quantum number by the simple formula. In some sense, well, sometimes people call those operators protected operators. And the crucial factor is that the conserved current of the flavor symmetry contains in this modifier. For some of you heard my talk in Tuesday, I also talk about representation of 4-dimensional n=2 theory, n=2 CFT, which is close cousin to this 5D theory. In that case, we have a lot more interest, more class of half BPS operators. But for 5D, that's about it.
So the flavor currents are for R equals
2.
R equals 2.
Yeah.
Okay.
So R plus 1 is like a free hyper. R plus 2 is containing the flavor current. So this is a I like to always study such set of BPS modifier, but for 5D n=1 theory, it's very simple. We don't have too many to study. And now we study deformation. Deformations. So given any quantum field theory, especially supersymmetric field theory, to understand the property of the CFT itself, I like to deform it to study what kind of deformations we can have. Again, for those theories, 5D n=1 theory, the deformation theory is also simpler than 4-dimensional n=2 cousin. For example, the relevant deformation and the marginal deformation are completely classified using the representation theory of conformal algebra. And the conclusion is that there's only one type of relevant deformation, so this is a mass deformation. Where M is real. That's all, and then there's no exact marginal deformation. But they're all isolated, there's no conformal manifold whatsoever. So again, it seems very simple. This is one type of deformation. For supersymmetric theory, we have another kind of deformation that is achieved by turning on web of some operators. So this is also special for supersymmetric field theory. So usually we have continuous model space of vacuum. And for 5D n=1 theory, we have the following vector structure. So I have a Coulomb branch. So here's the interesting part. So for 5D n=1 theory, the Coulomb branch is not parameterized by the web of some BPS operator. The reason is very simple. We don't have well, on this branch. There's no the asymmetry doesn't act on. So, but we don't have a non-trivial half VPS operators with without SU2R symmetry. So that makes a sharp comparison with the four-dimensional version. The four-dimensional N equals 2 case, the Coulomb branch is parameterized by the value of the BPS operators. So once you know the half BPS operators, you know the dimension of the Coulomb branch. But for 5D theory, even if you have understood the full set of half BPS operators, you don't know the dimension of the Coulomb branch. So that's a difference. And also
is there a constraint on the geometry of the Coulomb branch?
Yeah, I can talk about it.
Oh,
yeah,
oh, okay.
I can talk. So the geometry of the Coulomb branch looks like follows. The next
just maybe it's not relevant for what you're saying, but instead the Higgs branch is interpreted it's believed to be basically the web of the D2.
yeah, I'll talk about the Higgs branch. Yeah, I'll talk about that.
The D2 or just the D type operator?
D type of
The type of
yeah.
oh, I see. Okay.
Not just T.
D greater than equal to 2.
Yeah.
So D2 is the analog of
B1,
B1.
Yeah, we have to. So the Coulomb branch looks like a cone. So we use some real coordinates phi to parameterize the Coulomb branch, and it looks like a cone, and we can turn on deformation. Those relevant deformation, and without lifting the Coulomb branch. So mass deformation. Deformations do not lift the Coulomb branch, but they change the infraphysics. So therefore, the Coulomb branch actually should be parameterized by some set of real number corresponding to your Coulomb branch and then the mass parameter.
So it's no longer a cone once you turn on the mass parameters?
Well, you can always, take mass to 0.
Yeah, no, that's
Yeah.
mass is non-zero.
Yeah,
It's
mass is
deformed
non-zero.
into-
Yeah, deform it. Yeah, exactly. Yeah, I take them on equal footing. Okay, so the Coulomb branch has some interesting physical questions that we want to answer. So the first question is that low energy effective action. There's a genetic point the low energy is just a beating U1 A series, where this R is the dimension of the Coulomb branch, the number of phi's.
The real dimension.
Yeah, real dimension, yes. Real dimension. And the no energy effective action is determined by a pre-potential. So we like to determine the pre-potential, which is just a cubic function. Okay, this is vastly different from the 4-dimensional equals 2 case. So because the 5D equals 1 supersymmetry, the pre-potential can only be at most cubic form, while on the for 4-dimensional n equals 2 theory, the pre-potential can be very complicated.
So these are in some special coordinates, phi, which are the so those are the scalars which are related by supersymmetry to the U1
Yeah,
field
exactly,
strengths.
exactly. Yeah, those are scalar in the vector multiplier of this U1 RGC. M is related to the mass family, yes. Now, BPS states.
So, as before, the sort of the second derivative of f with respect to the phi's
Yeah, to give you the effective coupling.
gives you the effective
Yeah.
U1 coupling.
Yeah, including the mixing. So second derivative of f over phi I phi j
Right.
gives the GI. BPS states. So those are I call it the massive BPS states. They are the generic point, except the massive sector. You could have the massive BPS states. So we could have particles that it could be double boson or instantron particles if you have a Lagrangian description. But here I don't want to just call them double boson or instantron. I don't want to distinguish them. They're actually indistinguishable from the CFT point of view. And the crucial thing is the central charge can be is related to the coordinates, phi's, and the m's. So this is very much like a 4-dimensional BPS formula. BPS formula of 4-dimensional equals 2 theory. And then we have the strings. So that's a different thing from the 4-dimensional equals 2 pattern. So those strings are 2-dimensional objects. And their central charge is given by the due coordinate, which is defined using the pre-potential. So both the particles and the strings can become massless at the CFT point. And then because of those BPS states, the Coulomb bench have a singular locus. So there will be some singular loci where the particles and the strings become massless. Oh. this is the locus where we have a new massive particles and then new physics coming in. So in particular at the boundary, we could have many new, for example, enhanced gauge symmetry, and sometimes we can have an interacting CFT. So we'd like to understand those singular locus.
And those in general are codimension one, right?
Yeah, generally codimension one, yes.
So, in addition to the effective coupling for the U1s, is the kinetic term for the phis also given by second derivatives of this pre-potential? Or, in other words, do we also get, in other words, is this to determine a metric on the Coulomb branch? And are those singularities then metric singularities? Or?
I suspect not. Since those are all like topological, so it's a discrete number. But okay, so I guess the special when you have some singularity in the Coulomb branch, that means this there's a jump on this discrete number.
What discrete number?
Those are just discrete numbers, and not the continuous variables, continuous coefficients. So this gives us a Chern-Simons number. Chern-Simons coupling, 5D Chern-Simons coupling.
Are you saying the CIJK are integer values?
Yeah, integer, or quantized.
Are these just the triple intersection numbers?
Yeah, triple intersection number. I'm
okay.
Yeah, totally. So all the data here is discrete. So only they have a discrete jump. So those BPS particles or masses of BPS particle calculum modules into different chamber. Within each chamber, those data are constant.
I see. So you find the jumps from where you have zeros at the central charges, and on there, those are places where you actually have to. These are the different chambers.
Yeah.
You need a different pre-potential.
Yeah, exactly. So this is not a. So this pre-potential is is not a function which is valid on all the points of the Coulomb branch.
Mm-hmm.
It's just a piecewise constant stuff.
Can I ask just a follow-up question to Phillips? I mean, you should be able to answer the question of whether these are metric singularities in the moduli space or not, right? I mean, some of them, depending on how singular you make the geometry, some of them will be at finite distance and some of them won't. Do you know?
No, I don't
how
have
to
the
characterize?
concept about the finite distance or metric. So this is just topological data.
So because these vector multiplets aren't in BPS
Yeah.
states, it
Yeah.
could be that it's more like n equals 1 in 4 dimensions, where the Kähler terms, the kinetic terms of the chiral multiplet, the things that determine the metric on the moduli space are not protected, and so you don't have. So we don't know how to compute them a priori in a strong coupling situation.
Yeah, I have nothing to say about the Kähler couplings.
But didn't you say, maybe I didn't, you said it was constant? No.
What?
No, the pre-potential, I think, if we're saying the pre-potential doesn't determine the kinetic terms.
Does not
or the
determine.
metric.
Yeah.
But then your question remains. You may see one of these singularities or jumps, but it may actually be at infinite metric distance.
Yeah. Yeah, I have nothing to say about that. Okay, so now questions on Coulomb branch. So given a 5D n equals 1 CFT, I want to know the following thing. So the first question is I want to determine the flavor symmetry That is the carton part, so I know the dimension of the mass deformation part and the dimension of Coulomb bench. Parameters. So this parameter seems difficult to determine because they're not related to the protected operators. So given a safety, I like to determine those numbers. So just the dimension of this cone.
Not the dimension as in the number of dimensions. You want to say the scaling dimension.
No, there's no scaling dimension
Okay.
here. Yeah.
Okay, so you're just saying
Yeah. How many?
How many?
Yeah. Because I don't know.
Because the scaling dimensions, that's the metric information.
Yeah. I don't even know what kind of operators parameterize in the Coulomb.
Right.
Yeah, so it should be some operators, but I have no idea what they are, but they're not protected operators.
Mhm.
So this is a question that I'm not sure how to answer that. And then I'd like to know the pre-potential. Piecewise constant the pre-potential. Not just one pre-potential, we have many pre-potentials. They patch together. And then that's also related to the following question, the chamber structure of the Coulomb bench. Finally, I also like to know the physics of singular loopers. Another interesting question would be, we can compactify our 5D theory on circle.
What do you mean by the physics of the singular loop?
So what kind of particles or
becoming
BPS states become massless, and what the effect of physics on those singular loopers. Yeah, like I did for 4-dimensional. And finally, we can put the 5D theory on a circle, and we get a 4-dimensional n+2 theory at the infrared. But still, if we keep the size of a circle finite, the 4-dimensional n+2 effective theory would depend on some of the remnants of the 5D physics. So we like to understand the Coulomb bench of 4-dimensional n+2, corresponding 4-dimensional n+2 Sarvatin curve, and study the physics of that Coulomb bench. So when we do that, when we do the circle complication of Coulomb bench, the dimension of Coulomb bench is double. So it's no longer a real cone. So the physics seems much more interesting because we no longer have this constraint on the pre-potential. I guess in the 90s, Microsoft used this type of idea to learn how to derive the 4-dimensional, Sarvatin solution using the 5D theory. So that's Coulomb bench, but we also can have another bench. So we could have a Higgs bench, which is parameterized by the D-type operators I just mentioned, and then they could come out of the origin of the Coulomb bench. The question here is to determine the chiral ruination. and also we could have a mixed branch, which could come out of the singular locus on the Coulomb branch. So they intersect with the Coulomb branch by some lower dimensional submanifold on the Coulomb branch.
And does the mixed branch have a Cartesian product
Yeah,
structure?
I think so, yeah.
Also
Still,
has
yeah,
a
yeah.
non-renormalization, right?
Yeah, also I couldn't have a easy proof come out of my mind.
Mhm.
Should be followed from the surface image. I don't have too much to say about those two questions. We just talk. Okay, so those are the general aspects of five-dimensional anchor-swan theory. But you might ask, is it possible to find such theory? But it's quite counterintuitive to some of our standard training in quantum field theory. So we usually would like to start the Lagrangian, and then 5D gauge theory is non-renormalizable. So how we're gonna get a CFT? I'm gonna just review some of the constructions in the literature. So the first original way of finding this series through the gauge theory description. So this is a cyber work. So what Nati found is that he looked at the SU2 with NF less than 7 fundamentals. So those cases are non-renormalizable and IR-free. So infraphysics is not very interesting, although you can still study the Coulomb branch and study the prepotential. But what Nati asks is the following question. Let's take the gauge coupling to infinity, and can we find a UV fixed point in the sense of Wilson? And what Nati told us that there is a CFT, and moreover, it has a enhanced E-type flavor symmetry. So this infrared theory has a SO2NF times U1 flavor symmetry. So this SO2NF is related to the Euro flavor symmetry of the fundamental flavors, and this U1R is related to the instanton current. But this symmetry is enhanced to E-type flavor symmetry. So that's the inside of great insight, not the inside of cyber.
And what happens when NF is larger than 7?
What Nati claims is that you cannot get a UV fix. There's no UV fix in the sense of the so give you
About smaller than 5?
What?
Maybe it's NF is between 5 and 7.
Yeah, it's possible because in 5D we don't have this asymptotic frequency.
No, but
So there
but
there is
E and
there is an E1, E2, and so forth. Those are just names.
okay.
Yeah, just
But-
names. So
but-
E1 is like SU2, something like that.
I see.
No, I think E1's is more mysterious. It's
Yeah. U1 or maybe U1.
no,
Well,
Oh,
people
okay.
use a different name. Some called E1, E1 tilde.
uh huh.
Yeah.
Yeah. Okay.
Okay.
Alright.
So I'll give you a simple example which I'm gonna use a lot in the following talk. So pure SU2, very simple. So without any matter. The free potential is also easy to compute. Now find the Coulomb branch parameters, so which is what? In this null energy description, phi has a description, just a trace of say the real scalar in the vector modifier. And M0 is just a gauge coupling. And what Nadi argues that when phi to 0, M0 to 0, you get a safety. And in this gauge point of view, the Coulomb branch looks like this. 0, phi. So when phi equal to 0, so we get the SU2 flavor with the finite gauge coupling. And we take M0 to 0, we get the CFT point. But later I'll show you this picture need to be modified from the geometric point of view. Okay, just the gauge theory description. So in the original paper of Seibert, Etrudicate, and Morrison, they studied the generalization of this kind of gauge theory description. They consider all kinds of gauge group. And I think they made a mistake in the paper. They claimed that the pure gauge theory is not possible. I think one of the reasons perhaps that they missed some of the contribution from the to the potential from the instanton particles. That's probably one mistake. The other mistake is that the Coulomb branch, the structure of Coulomb branch seems so much more complicated than what they thought. They thought it was a single branch, but there were many phase transitions. No, you shouldn't call phase transitions. There were some chambers. So the potential is not a single value function. We'll see.
I don't understand this picture that you've drawn,
Yeah.
psi and m naught.
Yeah.
In this theory, there is m naught not equals 0.
Yeah.
Doesn't matter what value you take it; they're all the same theory.
Yeah.
And then there is some kind of limit as you set m naught to 0, which
Yeah.
is going to be the UV fixed point.
Yeah, both to 0, phi.
So there's a conformal field theory.
Yeah.
That's the m, right? The UV fixed point.
Yeah.
With a Coulomb branch,
Yeah.
psi,
Yeah.
sticking out of it.
Yeah.
And then there's an infrared free fixed point. That's the finite m theory. That's a disconnected. I just don't know what this picture.
So look at, take M0 and psi as your parameters with over the IR meaning.
Okay.
Because we have a
So that whole M0 axis with psi equals 0 represents a single infrared free fixed point, the SU2 Yang-Mills theory in the infrared.
well, yeah. Well, the theory is SU2 theory, but let's see. Some of the physics still depend on this value. For example, the central charge.
That's the only scale in the theory.
Yeah.
So it
double
all
boson.
scales with the M0 as, depends on the dimension, or just by engineering dimension.
Yeah.
So there's no real dependence on M0. It's either M0 is 0,
Yeah.
that's a UV fixed point, or M0 is not 0. in which
Oh
case
yeah, yeah,
it's the
yeah,
infrared
exactly,
pulse
exactly.
wave.
That's right, that's right. But I think the as another point where you get a U1 gauge theory, the physics still depends on M0 and the phi. Because you have the contribution from the also the central charge of the BPS particle also depends on this parameter. So it's not that like you can scale it away.
There's a ratio of psi to M0, certainly.
Not just ratio. So from the UV point of view, you have a SU2 flavor symmetry. There's a U1I flavor symmetry which is enhanced to SU2 in the UV, and you can turn on the mass deformation. Just one parameter to our Coulomb bench, and then we have another deformation. So that's Coulomb bench deformation. So those are two-dimensional Coulomb bench.
So, but that's not M naught. You're saying that the conformal field theory has another mass parameter.
Yeah, yeah, yeah. That gives you gauge coupling. At the depend on the one particular direction of the deformation.
Uh-huh.
Yeah.
Okay, but anyway,
Yeah, so
sorry,
so
I'm just confused.
that's a gauge theory. Version. Now, and then apparently it's not so easy to study that using field theory. And then people engineer many for the anchor safety using PQ5 construction. And then it could have to be string theory on PQ web, PQ5 web, and these people are Harmony, Anani, and Oh. So later explain what this means. So roughly it's a engineer some 5-brane PQ5-brane web, and then claim that when you take the limit or the error or the size of scale away, you get a CFT. And they also get many interesting physics out of it. The third approach is using M theory on threefold singularity. So this is the written. So what he told us is that if you look at a threefold with some divisor, and we look at the limit where this divisor to be vanishing, or it has a vanishing divisor. So we can have a M2 band wrapping on some of the cycle inside D. So when D to 0, we get masses of particles. And we can also look at M5 band wrapping on this divisor. And when D to 0, we get the masses or tensionless string. And at that moment, in Witten's paper called phase transition in M and F theory, he doesn't really claim that there's a local field theory, local interacting CFT at this point. He just claimed that since we have such a the existence of the masses of particles and masses of strings simultaneously, it has to be interacting that way. And then later, Cyber claimed that it's just a CFT, local CFT. So this is I guess this is a Paul string theory. So I'm going to follow this approach, and then later on we cover those two approaches. So I wanted to study the following questions. So let's conject that we can get 5D n equals 1 theory using M theory on threefold singularity. Then to classify 5D n equals 1 CFT, at least for some class, I'm not claiming all of them, but for this classes, to classify 5D n equals 1 CFT, it's equivalent to classify singularities. So we kind of take a reverse point of view. We take a singularity as a definition of CFT, and then understand its model space by studying the deformation of the singularity. So from Witten's point of view, he actually started with the Coulomb bench and then look at the UV fixed point. So I'm doing the reverse order. So I first define my theory using singularity, and then I try to study its resolution actually in this case. So this kind of motivated from our previous work on the classifying 4-dimensional angles to CFT using singularity. So in that context, we studied the type 2B string theory on singularity. And the Coulomb branch of 4-dimensional angles 2 theory is related to the deformation of the singularity. And now, for 5D,
the resolution of, oh, I'm sorry.
Deformation. Previous is
Oh,
deformation. Now it's
resolution.
resolution.
Okay.
So for M theory on singularity, Coulomb branch is described by resolution of singularity. Because for resolution, we're gonna get some exceptional divisor, and then we get the Coulomb branch by, and there's some cycle inside the divisor, and M theory has the 3 forms, self-dual 3 forms, so we get gauge field in the infrared. We also get particle and strings. And for the deformation of the singularity, we only get 3 cycles. So it's not gonna give us the Coulomb branch in this setup.
Is a Higgs branch seen geometrically in this?
It should be related to the deformation of the singularity. But I don't have a good story for that yet. Okay, so what kind of singularity? Again, I have many clues, but right now I don't really have a proof, but there are many indications that we're going to study the following singularity. So the first thing is just to look at the geometrically. So look at the degeneration of Caviar-3 manifold. So suppose we have a M theory on some compact Caviar-3 fold we get 5D angle-swarm supersymmetry, and we tune the module space, and try to say what kind of singularity we get. We can either tune the Taylor deformation or complex structure deformation, or even we can take some metric limit called the form of Hausdorff limit. So in all the speech generation study, it seems that we're going to produce a singularity called the canonical singularity. I'm not going to explain what exactly this means. One thing that I want to mention is that this is a generalization of the two-dimensional ADE singularity that people have studied a lot. So it's a similar class in 3D. So analog of two-dimensional ADE singularity. And those singularities have studied by Marsry in 80s in the context of minimal model. But I do want to give you some examples so you can have a feeling about how large this class of singularity is. So I have the quotient singularity, which fitting into this class. This is the study. This class of model has been studied by string theory in many different contexts. And here G is a finite subgroup of SL3. So a total for 17 or something. The lot of such singularities.
So, and is there something about the action of G that you have? Is this? Are they all have to be isolated?
No, not
No.
necessary. No, here no. And I'll say the toy Einstein singularity. So some people like to call the Calabi-Yau singularity, but it's actually Einstein singularity. And could have some certain hypersurface singularity. So, which actually are those that we studied in the four-dimensional inclusive context.
The certain means
With, it has to be
weighted.
canonical.
Oh, okay.
Yeah. And then,
But not necessarily isolated,
yeah.
and admit a weighted.
Yeah, sister action is also not required.
Not required.
It's not required. Oh, because
There's no.
you wanna.
No.
There's no you
So can you imagine what canonical means?
Means it can be defined using resolution. So it depends on the resolution property. Yeah, I can tell you more details later, but it's not. But I want to introduce the mathematics here.
Very
So-
loosely though, you're worrying about stuff that's going to be prevalent, right? You just want to preserve the Calabi-Yau condition under resolution. But
Yeah, that's kind of necessary. But
You're
turns
basically
out,
lifting all the requirements that you have in 4D, you basically lift them all.
yeah, but yeah.
Except for this canonical
But
part.
no,
So
have
for-
totally much weaker
Yeah.
justify an argument from the physics point of view. But turns out that everything will be consistent. So
And
there must be a physical
Is there a
reason.
physical way to understand why you don't require that the singularity is isolated? I mean, that's not
Isolated is not a requirement.
It
Well,
wasn't
even
in
4D,
even 4D.
Yeah, I don't
Right.
think it's as a requirement. Just we don't know how to study them for deformation, but for resolution it's much simpler.
Oh.
And then we can study cone over the puzzle surfaces So those are the examples which already studied by Seberg. So this will give us the E-type CFT. But more generally, we can study cone over so-called log diapazole surfaces. So we don't need to assume the surfaces to be smooth. We can have some singularity, and as long as we just consider this set of log diapazole surfaces, the cone over it will be canonical. So there seems a lot of such singularities.
Are these non-overlapping categories, or are they overlapping in some way?
Little overlapping, I would say. So each of them are quite distinct, those 4 classes. There are very few overlapping. For example, the toric ones, it could be hypersurface, but they're just a couple of examples. Most of them are just distinct.
Could I ask 2 quick questions to you? So one, I mean, as you mentioned in the minimum level program, canonical singularities, log canonical singularities are well understood. So in principle, one understands there is a set of these. The set is bigger than what you're saying, and some of these can be very hard to write down explicitly. When you say classify, do you mean that you're exhaustively going to try to somehow consider every type of log canonical singularity in a Calabi-Yau, or just within these families you're taking examples?
Or conjecture is that every 3D canonical singularity define 5D angles one CFT.
So that I
yeah, that's what I
understand,
mean
but
by
the question is about
classification.
enumerating. I mean that's.
Oh, it's
why-
impossible to enumerate all of
Right.
them. Yeah.
So when you say classify, you just mean there is some set, which I don't know how to write down, but in principle, every one of them should be.
Yeah, exactly.
And as-
Exactly. Yeah.
Okay,
Yeah,
and
well,
then
yeah.
One further question.
Yeah.
We know of examples in F-theory in 6 dimensions,
Yeah.
where you can have singularities that are non-crepant, and for which deformations can be obstructed, but they're still legitimate regimes of the effective theory. So it seems a good conjecture. I guess I'm asking, do you have any understanding of non-resolvable things in the context of?
Well, some of them are actually not resolvable. Terminal singularity, Q factorial terminal singularity is not resolved. It's not resolvable. There's no Krappan resolution. So we could simply interpret that as a say resolved Coulomb branch. Well, I don't want to claim it's all, so it's just this class. Yeah. Okay, so let's now.
But by the way, even back in that original Seiberg analysis of the
Yeah.
SU2,
Yeah.
and looking at the flows among that EN
Yeah,
series,
yeah.
wasn't there a flow from the E1,
Yeah. Yeah.
the one that
Yeah,
you
yeah,
were trying to
yeah,
describe?
yeah.
It actually flows to by turning on the mass, another fixed
Yeah,
point,
yeah,
what
yeah.
people call E0,
Yeah,
which
yeah.
it's a little mysterious and it doesn't have any Coulomb branch, would be.
It has Coulomb branch, a one-dimensional Coulomb branch.
The E0.
Yeah, I'll tell you what this theory, what that theory is.
Oh, okay.
The many, well, those classes are less studied. All of them are barely studied. Although I guess people know that, but surprisingly, not a systematic study of those series. So I'd like to just start with the toric Gorenstein singularity and tell you how to compute various interesting quantities on the Coulomb branch just from the geometry. So I'll talk a little bit about toric geometry. So we can fix a 3D lattice and so and a toric singularity, since I only care about the the singularity, the torque varieties I need to care about is just F1. So the torque singularity is specified by some set of primitive vectors, lattice vectors, or lattice points. And we can form a cone sigma so this cone is close. So and from this cone, I can construct what this alpha variant is by writing down the ideal. But what you just need to keep in mind is such a combinatorial gadget give you some variety, toric variety actually. And for Gorenstein singularity, it just means there's a basis such that the generators are all at the z=1 plane. So in this example, that means you use a z=1 hyperplane, and all the lattice points that you use on the z=1 plane. So mathematicians prove that such a cone give you a toric Gorenstein singularity. And because of this z=1 condition, so we can forget about the cone and just look at this z=1 plane, and this convexity condition means that we get a two-dimensional convex lattice polygon. So therefore, we can replace this three-dimensional combinatorial stuff with a two-dimensional convex polygon. So the classification of toric Gorenstein singularity becomes the classification of the two-dimensional convex polygon up to the GL to Z transformation. So not all of them are equivalent. So here's some of the example. Which so there's all the some of the examples that you have, and so therefore, at least from the classification of the toric type, the classification of 5D n=1 theory reduced to the classification of such a convex polygon. It turns out there were for the polygon with one internal point, which I later will tell you the number of internal points, give you the dimension of the Coulomb bench. So there were 16 type of convex polygon with one internal point, and 45 polygons with two internal points. So rank 1, rank 2 kind of classified in this context. And this singularity will give you the E0 state.
Are they allowed to have points along, I mean,
Yeah. I can give you a model number. When there's no points on the boundary, it's isolated singularity. When there are points on the boundary, then it's a non-isolated singularity.
so if you wanted an isolated but with no Coulomb branch,
Yeah, you would have that.
then
That corresponding to free matter. So you could have those kind of
that would be isolated then.
non-isolated. So as long as you have points on the boundary,
Yeah.
then they're not isolated.
Right.
Yeah.
But if you wanted it to be isolated, then there's only a couple that you could write down.
Yeah, well, actually one. Because there's no points inside, and then there's no point on the boundary, then there's only one smooth point, basically.
By point on the boundary, you mean not at the corners?
No, the opposite.
You include the corners.
Yeah. And those are the points on the boundary. That's what I mean. Okay, so
But this is, the Torrey-Gorenstein is a subset of the singularities that you expect to give 5D CFT.
yeah. Just
So it's not fair to say that you expect to have 45 rank 2.
Oh, just within this class. Yeah. Okay, so let's read some of the physics from it. Just we can get some immediate physical information out of this diagram. So before that, I want to study, give you a little bit fact on the geometry. So first of all, there's a so-called orbit cone correspondence. So essentially, it tells you that the k-dimensional cone in sigma give you a n minus k-dimensional let's see, torus invariant orbit in your variety. So from this example, from those examples, that means each point from the two-dimensional lattice polygon point of view, each point give me a one-dimensional cone. That means each point represents a divisor. So each boundary, so in this case, I don't have an internal generator. So each boundary, I mean, on the corner, the next point on the corner give me a divisor, although in this case it's non-compact. But in general, we're gonna get compact divisor. And each edge on the polygon give me a two-dimensional cone, and that give me a curve. So forget about the three-dimensional picture. Means a lattice point give me a divisor, a edge give me a curve. And the singular locus and the singular type can also be read from the toric diagram. So the conclusion is quite easy. For H, with D internal points we have a AD singularity. So that means we get a A2 singularity on this curve, as I just told you. So each edge gives you a curve, and there's A2 singularity on this edge, and also an A2 singularity on this edge, and A2 singularity on this edge. So we can immediately get rid of the flavor symmetry by noticing the fact that the empty on AD singularity give you a AD gauge symmetry, and since this curve is non-compact, we get the AD flavor symmetry. So each boundary gives you some non-abelian flavor symmetry. So for example, in this case, we get A2 times A2 times A2 flavor symmetry. But those symmetries could be further enhanced, which you cannot easily say from the geometry, but it could be further enhanced. So that requires further study.
So this is the minimum kind of flavor symmetry.
So this is the manifest symmetry you can rid of just from the geometry. It could have a further enhancement.
And the enhancement can even increase the rank. Or?
No, rank is rank. I'll tell you the rank. How to rid of the rank. So that's a flavor symmetry that I want to know. And in general, the number of mass parameter is equal to n minus 3, where n is the number of lattice points on the boundary. So for example, for this two example, there's one mass parameter, and for this example, there's no mass parameter. And number of Coulomb range.
So in this case, on the boundary, you mean on the vertices?
Yeah, vertices. Lattice points.
No. So in your A2 cubed example there,
Yeah.
then you say
You have 0.
no. It's
1, 2, 3, 4, 5, 6.
It's 9 minus 3 is 6.
Yeah.
But on another one, which was like say a quadrilateral with
4 minus 1.
let's make a big square with A2s on the thing.
Yeah.
You would say the flavor symmetry includes A2 to the 4th.
Yeah.
However, the rank is not 8 but 9.
Yeah.
So there's actually a missing sort of generator. The
Oh.
flavor symmetry is a rank higher than the A2 to the 4th that you identified that way.
Why
Yeah,
would it be a 9?
Yeah, exactly.
Because there would be a total of 3 times 4, 12.
Oh, you're right.
Yeah,
I see what
minus
you're
3.
saying.
Yeah,
Oh.
there's abelian ones from the corners.
So I see. So there's kind of a U1 for each corner minus an overall U1 cubed,
Right.
which is the
Yes.
toric action.
Yeah. There's some rotation. But from the geometry point of view, it's just the rank of the divisor class.
Uh-huh.
And the number.
But do you know that is it a factual thing that those extra mass parameters that you come from like the vertices are U1s or not? Do you know that those are U1s?
Genetically, it's a U1, but it could be further enhanced. The
Could be.
full enhancement, I couldn't tell just from geometry.
That's no more than saying that. That doesn't have any more information than just saying what the rank
The
is.
rank.
Yeah. I just tell you the rank. And then some of the enhanced non-abelian flavor symmetry just from the.
That's
gradient.
but that's actually
Yeah.
that gives you
That's all I can
slightly a
say.
little more information.
Yeah. That's all I can say.
Mm.
And the number of Coulomb range equal to the internal points. That is points. So this is rank 1. Okay, to answer the first question, flavor symmetry and the counting problem. Okay, now let's talk about the Coulomb branch. How to go to Coulomb branch. So we argue that it's related to resolution. Actually, it's related to Kraepelin resolution. So now the geometric fact about Kraepelin resolution. So they are given, or it is given by the unimodule triangulation of the polygon. By that, by this unimodule means the triangles have the area 1, and that means there's only one type of triangle, which is a triangle without any internal points and any boundary points. So get a so here you get a triangulation. This gives me a different point variety without any singularity, and the corresponding resolution is Kraepelin. And there's also only one type of unique resolution. And for this one, we actually have two resolutions. Two different resolution. And the resolution is not unique and related by flop. So So the physical interpretation of the flop is that each Kraepelin resolution gives you a chamber of the Coulomb branch, and different Kraepelin resolution are patched together into a full Coulomb branch, and within each chamber, your potential will be different. I have 10 minutes. Okay, so in the last 10 minutes, I'll show you how to compute the pre-potential. And tell you when what kind of singular locus we have and what kind of physics associated with the singular locus. Pre-potential. So there's the elegant formula proposed by Seibert, Petriligan, and Morris. The formula is following. So where phi I just the Coulomb branch parameter, and the SI is a basis of a local divisor class. So I take about this example. Actually, people already shoot this long time ago. This geometry is related to the pure SU2 cases that I talked about earlier. So let's take a resolution and then try to compute this thing. So we have the divisor according to the object cone correspondence. Each lattice point give me a divisor, and the internal one is a compact divisor. And then we can compute the divisor class locally. I don't have time to say details, but it's a very easy computation. And then you get the following relation: d2 equal to d4, d1 equal to d3, and then e equal to minus 2 d1 minus 2 d2. So this is a divisor relation, and we can compute the triple intersection number. That's all the data you need to compute the triple intersection number. Now we can compute use this formula. From this local, the relation of the local class group, we get the basis of divisors are d1, d2. So we could compute the triple intersection number and the equipotential using this formula. And we want to change the basis using the E, and we try to interpret this E as giving you the Coulomb bench. So we change the basis a little bit. So we get 1/6 psi E minus m0 d2, and we get the expanded. So we get this potential, which is exactly the pre-potential derived from field theory, but there's a subtlety here.
So this cube means put in the basis of the local divisor class and take the triple intersection number.
Right.
When you expand it.
Right.
Okay.
Right. It's just expanded. For example, this is equal to phi cube e cube plus m0 phi squared.
Yep.
M squared minus. The other intersection, triple intersection number was 0. So you only get these two terms.
Right.
Yeah. And then you get this answer. But there's a subtlety here, which seems different from the Lagrange physics point of view. Is the range of phi and m0. And phi and m0 is related to the A and the B by following formula. So I haven't seen anything about the range of the Coulomb bench. Now I want to claim that the range of the Coulomb bench is identified as the Maury cone, the Nath cone.
What?
The Nath cone. It's a dual of the Maury cone.
Maybe I'm not really following 100%, but like, what about the intersection, the triple intersection between E, D1, and D2? That doesn't give you another term?
No, there was only E and D2.
Yeah, because I changed the basis here.
Oh, I see.
Yeah. So only E and the D2 related. Yeah.
Okay.
Well, a simple fact is that the only triple intersection number, the non-zero triple intersection number is if these three divisors are on a single triangle. the only
I see.
E D1, D2 equal to 1, but E D3, D1 equal to 0. So use those relations. You get this. So what is the last minute? I'll tell you how to compute the left cone. So it's quite simple exercise. Just not, I don't have enough time to explain it. Yeah, it's very simple calculus though. So what is the left cone? So take a basis of divisors. So in our case it's D1, D2. D1, D2, for example. And then consider a general divisor, A D1 is B D2. And choose the curve, choose the complete curves, means compact ones in our case. So as I said, the curve is associated with the edges. So we can take two curves, C1 equal to E intersected with the D1, and C2 equal to E intersected with the D2. So the left cone means the divisors such that D dot C1 bigger than 0 and D dot C2 bigger equal to 0. So that's the definition.
So what is complete curves or what now?
It means just compact ones. So if the edge is in the inside. Yeah.
Okay.
Yeah. And you compute that, you find the range of A and B. So the range of A and B is just A equal bigger than 0, B bigger equal to 0. So this is the nav cone. The meaning of the boundary of the nav cone is that there's some curve which you can shrink. So in this case, the one boundary associated with the curve C1, and the other boundary corresponding to the curve of C2, which you can shrink. And so I want to claim that the boundary, each boundary corresponding to some particles become masses from the low energy point of view. From the geometry point of view, just corresponding to some the curve become vanishing. Now, using this relation, just precise regarded as the Coulomb range, the Coulomb range deformation of the in the vector multiply, we get the range of the Coulomb range actually from low energy point of view is actually look at the follows. Not exactly the one what side tells us. So it actually looks like this. So in this range, it's described by the usual SU2 gauge survey. But in this range, it's described by a dual SU2 gauge survey. So from the low energy point of view, at this boundary, we get the masses W boson. At this boundary, we get a masses instanton particle with a charge 1,1. So there's a dual description in a different ranging. And from the original theory point of view, the corresponding masses particle are different. So this is like an electromagnetic duality in 5D. And from the geometry point of view, it's actually, the mass of the particle is actually 1,1. So this is like a electromagnetic duality in 5D. And from the geometry point of view, it's actually, the simple to say. So there's the SU2 description. If we just do partial resolution, so there's the SU2 gauge group here. There's one description, but we can do a different triangulation. That is a dual triangulation that gives you a dual gauge theory description. So just from this low energy point of view, this dual description means that the internal particle become masses in the dual description. So this is kind of a 5D duet that I want to interpret. Yeah, so it's a little bit quick, but if you're interested, I can tell you more how to compute all these things. So essentially, I can tell you the whole Coulomb range, and just by computing the curve resolution and the triple intersection number, potentials, everything can be computed. Yeah. The questions that I like to ask. So also including the four-dimensional subwritten curve can also be rate from the curve, and you can study all kinds of four-dimensional interesting four-dimensional physics.
Four-dimensional.
Yeah, you can put your 5D theory on a circle, and you can easily read off the subwritten curve. Okay, I think I stop it here.
Why don't we take a like a 5-minute break, start at 10 till, and okay.